Good morning, everyone. Today we're going to do a dot product with the Cartesian form of vectors. And to start off, we're going to derive what the formula for dot product looks like in Cartesian form, right, which is going to be different than the geometric because we're dealing with just coordinates and not angles and magnitudes. So as I guess a flavor of what this is going to be, I'm just going to flip screens for a second here. And you don't have to copy this down. Okay, but maybe in grade 10, depending who taught you the course, they may have taken a side here to show you where quadratic formula comes from. Right, so what we have here, right, my top line, this is the general quadratic, ax squared plus bx plus c. And I follow sequence of steps. We're just basically completing the square here. And if we do that on the general quadratic and complete the square, eventually we get down to that familiar quadratic formula. Okay, so I'm taking something I already know and manipulating it to get kind of a new formula that then becomes very useful. Okay, so that's what we're going to be doing to get at the dot product in Cartesian form. Okay, so we'll start with a diagram and put some labels on here. So we're going to call one of these vectors A and one of them B. And I'm going to add a vector C running from the tip of B to the tip of A. Okay, and there's my vector C. Okay, our starting point is going to go back to trigonometry. Okay, because in this setup, I have A and B and the angle contained in between them, and angle, C across from it. So this is the setup for cosine law. So that's what we're going to start with. I have the magnitude of C squared equals magnitude of A squared plus magnitude of B squared minus 2, magnitude A, magnitude B, cosine of angle theta. Okay. Okay, now very well, there's Waldo here. Spot the dot product in this formula. Okay, and it's kind of hiding right at the end there. Okay, there is magnitude A, magnitude B, cosine of theta. So our goal now is to rearrange this formula a bit to isolate dot product and kind of see what we come out with. Okay, so our first step will be to switch sides. Okay, so I'm going to bring the term negative 2 AB cos theta to the other side. So that becomes 2 magnitude A, magnitude B, cos theta. And then bring the C squared back to the other side. So I have magnitude of A squared plus magnitude of B squared minus magnitude of C squared. Okay. Okay, so I'll do a little bit of tidying here. On the left-hand side, okay, I'm going to call this is 2 times A dot B. Okay, because I know that's what dot product looks like. Okay, on the other side, okay, I've got 3 vectors here, but our dot product is defined in terms of 2 vectors, A and B. So I would like to make a replacement for C. Okay, so what can I replace it with? Well, if I look at my diagram, again, okay, C runs from the tip of B to the tip of A. So from our vector addition and subtraction, that is equivalent to A subtract B, right? When I subtract 2 vectors, I go from the tip of the second one to the tip of the first. So I can rewrite this as the magnitude of vector A minus vector B. Okay, now we have the stuff for magnitudes, so let's start running it through. Okay, so I still have 2 times A dot B equals, okay, how do we do magnitude of A? Okay, so as a little refresher on the side here, right, my formula for magnitude is magnitude of U for some vector equals the square root of U1 squared plus U2 squared. Now, in this equation, I'm squaring those things, so I really don't need that square root sign. for that step. Okay, so for magnitude of A squared, that is the same as A1 squared plus A2 squared. Okay, similarly for B, okay, that is B1 squared plus B2 squared. Okay, finally for A minus B, okay, this is going to be a little bit messy, but right, for A minus B, to create that vector, I would subtract the A coordinates from the B coordinates. So again, on the side here, as a reminder of what that would look like, okay, my coordinates for A and minus B would be A1 minus B1 and A2 minus B2, right? I just take the coordinates from A, subtract the coordinates from B. So my third expression there for magnitude is going to become, so I'm subtracting, I'm going to need a couple sets of brackets here, so hold on. Okay, and I know it's square brackets, it's not for vector, I just need multiple brackets here. So I have A1 minus B1 squared plus A2 minus B2 squared. Okay, so all these numbers, or all these, should say, variables on the right-hand side, right, A1, A2, those are all just numbers, they're coordinates. Okay, so now I'm going to just use some standard algebra to tidy this stuff up. So again, on my left-hand side, I still have two B. Okay, so what I'll have here, I have A1 squared plus A2 squared plus B1 squared plus B2 squared Okay, now inside this bracket, okay, subtract. Okay, I have A1 squared minus B1 squared. Okay, that's going to be using distributive property. Okay, so I would have A1 squared, right? A1 times B1 a couple times, so minus 2 A1 B1, and then plus B2 squared, sorry, B1 squared. Okay, similarly for the second one, I'm going to have A2 squared minus 2 A1, sorry, A2, B2 plus B2 squared. Okay, that's a lot of A's and B's. Okay, now we'll start putting things together. I'm going to subtract all these terms. So I have an A1 squared here, subtract A1 squared. That's going to cancel out. I have an A2 squared minus an A2 squared. That cancels out. Similarly for B1 squared and for B2 squared. Okay, so what I'm left with is these two terms here, okay, and I'm subtracting a negative, so they're going to become positive when they come out of the bracket. So I'm left with 2 A dot B equals 2 A1 B1 plus 2 A2 B2. Now everything is divisible by 2. So last but not least, I have A1 B, sorry, A dot B. So my dot product is equal to A1 times B1 plus A2 times B2. So out of that mess that we started with at the start, we have this remarkably simple formula for dot product. Okay, if I want to get the dot product of A and B, I simply multiply the first coordinates or the x coordinates together, and I multiply the y coordinates together, and I add them up, and that's it. Okay, that's all you have to do in Cartesian form. So here's a summary of that. Okay, if I have two vectors, A1, A and B, okay, and I'm using the Cartesian form, then the dot product of those two vectors is simply A1, B1 plus A2, B2, and that's it. Okay, so for a quick example, we'll show how that calculation works. So if I want to do the dot product between the vectors 1 and 5 and 7 and 9, okay, so I have 1, 5, dot, 7, 9. Okay, the way I do that is I'm just going to multiply the first coordinates together. So I have 1 times 7, and I'm going to multiply the second coordinates together. 5 times 9. Okay, and then I'm just going to total those up. So I've got 7. Wait a second, pardon me, I don't need these square brackets anymore. Okay, so I've got 7 plus 45, and that equals 52. And that's pretty much it. Okay, so here's two more. Take a minute and run those through, and pause the video for a sec, and we'll get the answers. Okay, so we're zooming now, and hopefully, okay, if I'm right, and you got the same thing here, for the dot product of negative 28 and 69, I got 32 as the answer for that. Okay. And for the next pair, for 4, negative 3, and 6 and 8, I got 0 as the dot product. Okay, this is an interesting one to note because we talked about this property yesterday. But because the dot product is 0, what does that say about those two vectors? They must be perpendicular. So if I draw these on a grid, okay, 6, 8, which would be something like this, and 4, negative 3, which would be down here, okay, those two vectors should be perpendicular to each other because their dot product is 0. Okay. All right, example 2. We're going to use the Cartesian form to verify commutative product. Okay, we mentioned this as a property yesterday. And again, this is another little kind of a proof, and we're going to prove how this works. So just to recap, what the property is, commutative property says that I can do u dot v, and that should be the same thing as v. Okay, so for this form of proof, we're going to do kind of like what you would do with trig identities. We're going to do left-hand side, and we're going to do right-hand side and see if they agree with each other. Okay, or actually, in this case, I think we can run the whole thing through, but let's see what we get. So I start with u dot v, okay, and I'm just going to use the definition. That is equal to u1 v1 plus u2 v2. Okay, and now I'm talking about numbers. Okay, so with scalars, I can also use commutative property and flip these around. So it would be okay if I said this was equal to v1 u1 plus v2 u2. Okay, so again, this is commutative property for scalars, right? When we're just working with numbers, we know that 3 times 5 equals 5 times 3. Okay, but now that I've done that, I notice that that's the form of the dot product the other way. So this is equal to v U. And we're done. For our last example, determine the value of k such that U73 and V5k are perpendicular to each other. So once again, there's our lovely property of being perpendicular. So if the two vectors are perpendicular, then I know already that when I do U dot V, I should get 0 if they're perpendicular. So now I just start writing dot products. Okay, so that means that 7 times 5 plus 3 times k should equal 0. And keep running it through. So that means 35 plus 3k equals 0. And now it's just a little equation that I can solve for k. So 3k equals negative 35 when I bring 35 over, and k equals negative 35 over 3, and that is my exact answer. Okay, of course, you can do quick verification by going back up to the top and multiplying it through and showing that they equaled 0. Okay. So thank you for watching and for slogging through that proof at the beginning. That could be a good one to put on a quiz or a midterm, by the way. Apologize for that little thing popping up there. Okay, so here's the practice work I want you to work on. Okay, so starting in the same section you were working in yesterday, just a few different questions from there. Okay, one last little tidbit I'm just going to throw in there, and I'm hoping a few students in the room who have taken data before might have recognized that. When I was doing dot product, right, like 35.21, and I multiply the first two coordinates and add them together, so that's 6, and the second two and add them together, 6 plus 5 is 11. That's basically the same as the matrix multiplication that we were doing in the final unit of the data course, right? The only difference being in the data course, I would have written this one sideways, okay, and we would have gone across and down. That might not mean anything to anybody else right now, but for those of you who've taken data with me, it's almost the same thing as that. All right, so again, thanks for watching. There's your practice work. Have a great weekend, and I will see you on Monday.